Okay, let's dive right into this explainer with a massive, literally paradigm-shifting statement from NVIDIA's CEO, Jensen Huang. He recently declared, AI now has to think. In order to think, it has to inference. The inference inflection has arrived. Now, this isn't just some catchy soundbite for a tech conference. It's honestly the starting gun for a total restructuring of how artificial intelligence is built, run, and integrated into our daily lives. We are crossing a critical threshold here, and today we're going to break down exactly what that actually means. So, welcome to today's explainer, where we're unpacking the massive ripple effects of this so-called inference inflection. For the last few years, the entire tech world has been hyper-focused on the lab, right? Just training these massive neural networks. But now we're finally moving out of the lab. The industry is shifting from just teaching AI how to learn to actually putting it to work in the real world. To make sense of this whole transformation, we've got a clear roadmap today. We'll cover the inference inflection, the completely surprising CPU comeback, the rise of AI agents, the open model price war, and we'll wrap up with the future of AI research. All right, kicking things off with part one, the shift from learning to doing. The biggest names in the space are basically signaling that raw training is no longer the only game in town. Sam Altman literally said, we have to become an AI inference company now. And Noam Brown, a super prominent AI researcher, pointed out that inference compute is a strategic resource that is currently totally undervalued. It's kind of like, think of training as sending an AI to college. It takes years and massive resources. But inference? Inference is the AI actually graduating, getting a job, and doing work for you every single day. Deploying and running these models is absolutely the new battleground. So we're transitioning rapidly through three very distinct phases of AI compute. We started in the training era that was all about brute force, GPU-heavy server farms just churning through oceans of data. We're now deeply entrenched in the inference era, where the models are already trained and we're just trying to run them efficiently to, say, generate text and code. But hold on, because we're already accelerating toward the third phase, the agentic era. This is where AI doesn't just answer your questions, it autonomously acts on your behalf. And making that leap, it requires a totally different kind of computing architecture. Which brings us nicely to part two, the surprising CPU comeback, and how we orchestrate the AI stack. When you look at the system architecture, the hardware shift is stark. Back in the training era, you had a massive 7-to-1 or even 8-to-1 GPU to CPU ratio. The GPU was the undisputed king. But as we move into the inference era, and especially this new agentic era, that ratio shifts dramatically toward 1-to-1. The CPU's role is growing significantly because the workload is changing from just crunching math to actively orchestrating complex tasks. So the crucial point here is understanding why this hardware shift is happening in the first place. Training required massive brute force memory bandwidth, literally just shoving as much data as humanly possible through high bandwidth memory. But running smart agents, that requires complex control, step-by-step logic, simulating software environments, and managing memory retrieval. These are all orchestration tasks, and handling the control plane is exactly what the traditional CPU was literally built to do. With GPUs being the absolute rock stars of the AI boom so far, propelling companies like NVIDIA to multi-trillion-dollar valuations, you really have to ask, is their absolute monopoly finally starting to crack under these new requirements? As AI starts to actually do rather than just learn, the bottleneck isn't just about math anymore, it's about logic. And hey, this isn't just some wild theory. In their recent Q1 earnings call, Intel's CEO stated directly to investors that they are seeing clear signs of the CPU reasserting itself as the indispensable foundation of the AI era. He points out that the backbone of AI computing in production still relies on a CPU-anchored architecture. Sure, accelerators are central to frontier AI, but the actual orchestration layer is driving immense new demand for server CPUs. Even within the accelerator space itself, workloads are fracturing. To handle massive inference demands, companies are physically splitting up the workload in a process called disaggregation. It's like, think of prefel as the AI reading a massive book and digesting your prompt. They might run that on one type of chip, like AWS Trainium. Then, the decode phase, where the AI is actually writing its summary out token by token, is run on an entirely different system, like a Cerebrus machine. The whole inference workload is becoming incredibly specialized. Okay, moving on to part three, software's new paradigm and the rise of AI agents. Building an AI that actually works for you isn't just about raw model smarts anymore. Honestly, a smart model in a vacuum is basically useless. The new requirements for user experience involve a complex harness.
This harness has to manage long-term memory, seamlessly fetch contextual data, and most importantly, orchestrate various tools, like your web browsers, your code compilers, or your databases. The software built around the model is quickly becoming just as important as the model itself.
Because of this, we're seeing a massive evolution in developer tools. Platforms like OpenAI's Codex and the incredibly popular code editor Cursor are pivoting hard. They're moving away from being simple autocomplete copilots and transforming into foundational headless agent infrastructures. Basically, they're providing the underlying runtimes that let developers build full-scale autonomous workflows that operate entirely in the background. It's a real game changer. Researchers are even formalizing this wrapper software into a brand new discipline called agentic harness engineering. It sounds complex, but basically it's a methodical process to optimize the software wrapped around the model. You create revertible components so the agent can basically hit undo on its mistakes. You provide condensed execution evidence so it knows exactly what it just did, and you use falsifiable predictions to test outcomes. Just by improving this harness, researchers recently boosted scores on the complex terminal bench benchmark from 69.7% to a massive 77.0%. The AI model itself didn't get any smarter. The harness just made it vastly more effective.
To show you how incredibly real and commercial this is getting right now, just look at Cloudflare. They are actually treating AI agents as legitimate software customers. They've built infrastructure that allows agents to autonomously navigate business workflows, create user accounts, register web domains, and get this, even start paid subscription plans on behalf of a human user. Vendors are exposing actual financial workflows directly to autonomous agents. Wild, right?
Part 4 is where things get really competitive, the open model price war. An absolute arms race is underway among the latest open-weight heavyweights. You've got Mistral Medium 3.5, which is this massive 128 billion parameter dense architecture built for heavy reasoning. Then you have IBM's Granite 4.1, which focuses on absolutely incredible token efficiency. To put that in perspective, it used just 4 million output tokens on a benchmark compared to a rival's 78 million. That makes it ridiculously cheap to run at the edge. And finally, strong open competitors like Lang 2.6 are pushing math and coding boundaries. Everyone is just fighting for maximum efficiency. And this single number right here perfectly encapsulates the results of this war. $3. That represents the plummeting cost per million output tokens for highly capable models like Qwen 3.5+. Just a year ago, this level of intelligence would have cost orders of magnitude more. High-end AI intelligence is rapidly commoditizing, making it economically viable to deploy literally thousands of agents to solve a single problem. At the exact same time, the middle layer, the software sitting between the models and the physical GPUs, is getting significantly faster. We are seeing major structural optimizations like Alibaba's Flash QLA, which dramatically speeds up long context workloads. Alongside sweeping updates to VLM, these optimization engines are slashing latency and boosting throughput, making serverless inference incredibly snappy for all of us. And finally, part 5. How do we actually measure true intelligence moving forward? There is a very provocative new research thread turning heads right now called Incompressible Knowledge Probes, or IKP. It's a fascinating methodology that tests models purely on hard, obscure facts to reverse engineer their actual physical size. The working theory here is that while you can teach a tiny model to reason or sound really smart through fine-tuning, you simply cannot fake raw, uncompressed, factual knowledge. And honestly, the data backing this up is staggering. Across over 1,400 questions and nearly 200 models, the data shows an incredible 91.7% correlation between factual accuracy and the raw physical size, the parameter count, of the model. It suggests that factual capacity simply does not compress over time. If you want an agent that actually knows the facts of the world without having to search the web for every single little thing, you still need massive, scaled-up models. So, as we prepare to deploy millions of these AI agents into the real world, to do our work, manage our systems, and even spend our money, it leaves us with this final, critical thought to ponder. Can model intelligence truly be compressed into tiny, hyper-efficient packages? Or will the raw, uncompressed scale of massive models always win out in the end? It is absolutely the question that will define the next decade of computing. Thank you so much for joining me on this explainer, and keep exploring.